Hello friends. Welcome to my channel. Ever wondered how a mobile charger converts 230 volts AC from your wall socket into just 5 volts DC for your phone? Let's break it down step by step. Step 1. AC input, that is 100 to 240 volt AC. Your charger is connected to the wall socket and receives AC, alternating current, power. What happens? Input voltage can vary from 100 to 240 volt AC. Frequency is typically 50 Hz or 60 Hz. This wide range allows the charger to work worldwide. Purpose is to receive electrical energy from the main supply. Step 2. EMI Filter, electromagnetic interference filter. Before entering the main circuit, the AC power passes through an EMI filter. Components are common mode choke, X capacitor, Y capacitor. What happens? It removes high-frequency electrical noise, prevents charger switching noise from returning to the power grid, protects nearby electronic devices from interference. Purpose is to ensure clean and stable input power. Step 3. Bridge rectifier. The filtered AC is sent to a bridge rectifier. Components are 4 diodes arranged in bridge configuration. What happens? AC waveform has positive and negative half cycles. The bridge rectifier flips the negative half cycle. Output becomes pulsating DC. Purpose is convert AC into DC. Step 4. Bulk capacitor, DC smoothing capacitor. The pulsating DC is not suitable for electronics. Components are electrolytic capacitor, typically 400 volts rated. What happens? Stores energy during voltage peaks. Releases energy during voltage dips. Smooths the pulsating DC. Typical voltage 230 volt AC to approximately 325 volt DC. Purpose is create a stable high voltage DC bus. Step 5. PWM switching circuit. This is the heart of the charger. Components are PWM controller IC. MOSFET. What happens? MOSFET rapidly switches on and off. Switching frequency typically ranges from 50 kHz to 300 kHz. High frequency pulses are generated. Why high frequency? Smaller transformer size, higher efficiency, less heat generation. Purpose is convert DC into high frequency AC pulses. Step 6. High frequency transformer. The high frequency pulses enter the transformer. What happens? Voltage is stepped down. Primary and secondary windings are electrically isolated. Example: 325 volt DC equivalent to 5 volts or 9 volts or 20 volts output depending on charger design. Safety benefit. No direct electrical connection exists between mains and phone. Purpose is isolation and voltage reduction. Step 7. Secondary rectifier. The transformer's output is still AC. Components are Schottky diodes, synchronous MOSFET rectifiers, modern chargers. What happens? High-frequency AC is converted back into DC. Purpose is convert transformer output into usable DC. Step 8. Output filter capacitor. The rectified DC still contains ripple. Components are low ESR capacitors. What happens? Removes remaining voltage fluctuations. Produces clean DC output. Purpose is provide smooth voltage for the phone. Step 9. Feedback and voltage regulation. The charger continuously monitors its output voltage. Components are optocoupler, TL431 voltage reference, PWM controller. What happens? Output voltage is measured. Feedback signal is sent to PWM controller. PWM adjusts MOSFET switching. Example: output drops below 5 volts, that means PWM increases power. Output rises above 5 volts, that means PWM reduces power. Purpose is maintain constant output voltage. Step 10. USB output to mobile phone. The regulated DC is delivered to the USB port. Typical outputs: 5 volt DC, 9 volt DC, 12 volt DC, 20 volt DC, USB PD fast chargers. What happens? Phone communicates with charger. Charger supplies required voltage and current. Battery charging begins safely. Purpose is provide regulated power to the mobile device. Hope you enjoyed this video and found it useful. Please subscribe to my YouTube channel for more electrical engineering content. See you again.